that's what's on my slide, Laura. Okay, so thanks for the introduction. And so this talk is kind of a shift from prebiotic chemistry to atmospheric dynamics. So let's all take a deep breath. And we're going to kind of get back into the headspace we were in this morning and maybe yesterday and Tuesday. So I'll be talking about the atmospheric circulation and climate of terrestrial planets orbiting both sun-like stars and M-dwarf stars. This is kind of following off of one of Martin's slides from this morning. And kind of one theme I'll come back on again and again is the effect of rotation on atmospheric circulation of terrestrial planets. And so here I'm showing you a plot from Adam Showman's review paper from a few years ago on terrestrial planets. And it's showing you the distinction between tropical regions, which are regions where rotation doesn't matter in the overall force balance. So the Coriolis force is relatively unimportant. And extratropical regions where the Coriolis force does matter, rotation is really important. And how that changes with planetary rotation period. So this goes from an Earth-like rotation period of 1 day, where we have tropical regions, and we have extratropical regions. And as we go to longer rotation periods, the tropical regions, the width of them widens. And once you hit a rotation period of about 10 days, the entire planet is now an all-tropics world, where rotation is relatively unimportant in the overall force balance. And so you can characterize this by the Rossby number of the planet. And so if the Rossby number, which is the ratio of advective to Coriolis forces, is large, then the Coriolis forces can be neglected in a global sense. And so you can see this directly in general circulation models of terrestrial planets. And so here I'm showing you two GCM results from Ravi Koparapu. So the top panel is showing you simulations of a Earth-like planet around a sun-like star with a 24-hour rotation period. And you can see that the planet has a hot equator and a cold pole and a large equator to pole temperature contrast. And the circulation, the atmosphere, is trying to erase this equator to pole temperature contrast. So that's what's driving the large-scale circulation, the Hadley cells and the Ferrel cell that I'll be talking about a bit later. But for the M-dwarf planet star shown on the bottom here, which is slowly rotating because it's tally-locked with a rotation period of about 58 days, you can see that the day side is really, really hot because that's where you're seeing the radiation, and the night side is cold. But the equator to pole temperature contrast is really tiny relative to the planet around a sun-like star. And this is because the entire day side of the planet is acting like the tropics. And one consequence of this is the cloud coverage in these two models, which is something that Martin talked about and something that was very important and potentially in early Venus that Mike Way was talking about yesterday. So for the planet around a sun-like star that has an Earth-like rotation rate, we have lots of clouds, as you can see here, near the equator, which are driven by deep convection in the tropics. This makes all the thunderstorms that are famous in the tropics. And you have less clouds as you go to higher latitudes, in a general sense. But for the planet orbiting an M-dwarf star that's slowly rotating, because there's deep convection throughout the day side, there's now a day side cloud fraction that's relatively high throughout the day side. And this high day side cloud fraction, as we saw earlier today in Martin's talk, acts to affect the habitable zone. So it makes the habitable zone potentially wider for planets orbiting M-dwarf stars that are tally-locked. So this is work of Jun Yang. This is his GCM results for slowly rotating planets in the red line, rapidly rotating planets in the black line, and then the other two solid lines show previous 1D models for the inner edge of the habitable zone as a function of the temperature of the host star, so later type stars going down, and incident stellar flux, so higher stellar fluxes going to the left here on this diagram. And you can see down near the bottom of the domain here in the M-dwarf region, the inner edge of the habitable zone for the slowly rotating and tally-locked models is about 50% or more closer to the host star in incident stellar flux than in the rapidly rotating models. So this is just one example of how rotation affects circulation and potentially affects habitability. And rotation affects circulation in other ways. But also there's a broad range, right, of planetary parameters that can affect circulation. You can think of things like the incident stellar flux, of course, the surface pressure, the gravity of the planet, the planetary radius. And so I ran a large grid of simulations of terrestrial planets orbiting both sun-like stars and M-dwarf stars that you can see in this paper that was published earlier this year. And so they use a kind of idealized model setup, even though they're using a relatively complex GCM, which is ExoCAM, which was the same GCM from the simulations I just showed you earlier of Ravi Koparapu. And so I'm using an aquaplanet setup with a nitrogen water atmosphere around stars that are either late type M-dwarf stars, kind of late K, early M-dwarf stars, or sun-like stars. And I'm assuming tidal locking if the planets are orbiting M-dwarf stars. And so due to time, I'm mostly going to be focusing on rotation period in this talk, a little bit about surface pressure. But if you want to learn more, you can check out the paper. So first I'll talk about the circulation of planets orbiting sun-like stars, and then move on to planets orbiting M-dwarf stars. So here I'm showing you results from simulations on the left-hand panel of a planet with a 1-day rotation period, same as Earth, and on the right-hand panel, a planet with an 8-day rotation period. These are zonal mean temperatures in the colors, and the contours are showing the zonal mean potential temperature. The potential temperature is a measure of entropy in the atmosphere, and I'll come back to why this is important in a little bit. And so the y-axis of these panels is the pressure normalized by the surface pressure, so the bottom of the panels is the surface, and then the x-axis is latitude. And so you can see that in the 1-day case, the equator to pole temperature contrast is larger than in the 8-day case. And additionally, in the 1-day case, if you look at the spacing of the contours, they're relatively more closely spaced. And as a result, the potential temperature lapse rate also increases with increasing rotation rate. And I'll come back to this later and talk about why it's important. So this is how the climate changes when you change rotation rate, go to slower rotation rates than Earth. But what happens to the dynamics? So this is kind of alluded to in previous talks. So the dynamics also greatly changes. So here I'm showing you the same parameter space on the axes, but now I'm plotting in the colors the stream function of the circulation. So the stream function tells you which direction the circulation goes. So if it's red, it's a clockwise circulation, rising at the equator and descending at higher latitudes. And if it's blue, it's showing a counterclockwise circulation. Again, in this case, because it's a Hadley cell, rising at the equator and descending at higher latitudes. And so you can see as we vary the rotation period, the width of the Hadley cell changes in these two models. As we decrease the rotation rate, increase the rotation period, the Hadley cell becomes wider. And additionally, I'm also plotting in the contours here the zonal mean zonal wind speed in the atmosphere. So this is showing you the east-west jets in the atmosphere. And so you can see that the east-west jets occur at about plus or minus 30-degree latitude in the Earth-like case. And these are the same jets that, if you flew here from the USA, made your trip a little bit faster, and will make your trip a little bit slower going back. It's going to be annoying. And you can see that if our planet was a slower rotator, these jets would occur at higher latitudes because these jets occur at the edge of the Hadley cell, and they're formed by a mixture of angular momentum conservation leading to jets, plus eddy interactions feeding into the zonal mean flow. Okay, so that's going to slower rotation periods than Earth, but what happens if you make it rotate faster than Earth? So here I'm now comparing maps of the circulation. So on the left-hand panel, I'm showing the zonal wind. So this is the east-west wind, and the right-hand panel is I'm showing the eddy zonal wind. So this is the deviation of the east-west wind from the zonal mean east-west wind. So the deviation from the east-west average of the east-west wind. That's a mouthful. So you can see, again, our subtropical jets at plus or minus 30-degree latitude, and you can see large-scale eddies that are driven by instabilities near the jet, and you can also see large-scale eddies in the tropical regions as well. And for the faster rotating case, you can see that we no longer just have two eastward jets, one in each hemisphere. We now have many, many eastward jets. And additionally, you can see that the length scale of eddies decrease with increasing rotation rate. This was alluded to earlier today. And so for faster rotating planets, we have smaller eddy length scales. We can fit in more zonal jets. And also, I'm not showing it here, but the equator to pole temperature contrast also increases with increasing rotation rate. So the question is can we explain this, how the large-scale circulation changes in a simple analytic way? And so I just want to introduce a concept here that I'll be referring back to. So what I'm plotting on this diagram, these different lines, they're isentropes. So they're contours of constant potential temperature in the atmosphere, or contours of constant entropy. And the y-axis here is height, going from the surface to the tropopause. And the x-axis is latitude, going from the equator to the pole. And so I'm plotting here one line, the red line, which has a slope that I'm defining as a slope of 1. So it's a isentrope that rises from the surface at the equator to the tropopause at the pole. And this is where Earth lies on this diagram. It has a slope such that an isentrope would rise from the surface of the equator to the tropopause of the pole. And so the reason why Earth is at this kind of state has been kind of debated over the past 50 years, since the 70s. So people think that Earth's atmosphere, if in a radiative convective sense, without dynamics, would be in an unstable state where the slope is greater than 1 and the planet would be unstable to so-called Baroclinic instabilities, which are the large-scale fluid instabilities that lead to weather and storms in Earth's mid-latitudes, where we are now. And so basically these instabilities will lead to an adjustment such that the planet would go from this unstable state back to the stable state. And so there's a wide range of literature on this. But relatively recently, Malte-Jansen developed a simple theory to explain that, in principle, if the forcing regimes are very different than Earth, the atmosphere can stay in an unstable state. It doesn't necessarily have to adjust back. So in that case, Earth just kind of happens to be in this slope equals 1 state. And note that if the slope is less than 1, then the atmosphere is, on a large scale sense, stable to baroclinic instabilities. And so note that if you have some sort of theory for this slope, in principle, you should understand how the equator to pole temperature contrast and the surface to tropopause potential temperature contrast depend on planetary parameters. Because this criticality parameter is directly related to the ratio of the horizontal potential temperature contrast and the vertical potential temperature contrast in the atmosphere. And so I just kind of want to show you in a basic sense what these two parameters, the horizontal and the vertical potential temperature contrast, mean in terms of the climate of an exoplanet. So here I'm showing you maps of zonal mean potential temperature. So these were the contours in my earlier plot showing the climate. And I'm highlighting the horizontal potential temperature contrast in the red. So this is basically just the equator to pole temperature contrast at the surface, because at the surface, potential temperature and normal temperature are the same. And the vertical potential temperature contrast is just the difference of the potential temperature from the surface to the tropopause in the mid-latitudes. And so we can try to figure out what the slope of an isentrope would be in this kind of atmosphere. So if we basically just connect the lines from where an isentrope or a contour of constant potential temperature is at the surface at the equator to the pole, you can see that it rises up to about here. So not quite the tropopause in this case. So this atmosphere is stable in a large-scale bulk sense to baroclinic instabilities because the slope of its isentropes across a hemisphere is less than 1. And so Malte-Jansen developed a simple theory to try to explain how the criticality parameter should depend on planetary parameters. It should increase with increasing rotation rate because baroclinic instabilities should increase in strength with increasing rotation rate because deformation scales decrease with increasing rotation rate. And it should also depend on the surface pressure of the planet, the tropopause height or the scale height, and many other parameters. And so here's just that scaling. So this is how the slope of isentropes depend on rotation rate, pressure, and then h, which is the minimum in this case of the scale height and the tropopause height. Note that Earth is in a state where the scale height is actually kind of similar to the tropopause height. It's just a little bit smaller, but in principle, it can be larger for a different kind of atmosphere. And so these are comparisons with my GCM results. So the solid lines in these plots are showing you the GCM results, and the dashed line is the scaling for the criticality parameter, the slope, as a function of rotation rate on the left-hand panel and surface pressure on the right-hand panel. And so you can see as a function of surface pressure, the scaling does a really good job throughout the full range of surface pressures we considered. As a function of rotation rate, the scaling does a good job for the fast rotating cases around here, but it doesn't do such a good job for the slowly rotating cases with rotation periods greater than about 4 days. And the reason why is because these cases down here rotate slow enough that the Rossby deformation radius is larger than the planetary radius. And so baroclinic instability shouldn't be very important in these atmospheres. And so this theory wouldn't apply to these slowly rotating planets. It only applies to planets with rotation rates that are kind of like Earth or faster. And so, as I said before, if we understand this slope of isentropes, we should also understand the equator to pole temperature contrast and the vertical potential temperature contrast. And in principle, the vertical potential temperature contrast can be related to the lapse rate of the atmosphere, which is something that we could, in principle, with a really awesome giant light bucket, actually constrain with retrievals on terrestrial exoplanet atmospheres, when I'm maybe 50 or something. Or older, we'll see. So here I'm plotting the scaling between the GCM and theory for the equator pole temperature contrast on the left-hand panel and the bulk lapse rate or the vertical potential temperature contrast on the right-hand panel. And you can see that the theory predicts that both of these should increase with increasing rotation rate, and our GCM results do bear that out. Note that this is kind of more of a broad agreement than the criticality parameter, but in general, the scaling predicts that this should hold over a wide range of parameters. And so we've also tested surface pressure, gravity, and planetary radius. Or you're holding up a sign? I have 20 seconds. Great. All right. So I think I'm just going to skip to the end. I talked a lot slower than I normally do. But so I've also looked at planets orbiting M-dwarf stars. And so the one thing I kind of want to get across is that for planets orbiting M-dwarf stars, we know that their cloud coverage should depend on the rotation period. So slowly rotating planets have more day-side cloud covers than fast-rotating planets. And in principle, with future observations, phase curve observations of these planets, we could actually distinguish between these. So for rapid rotating planets, which don't have significant day-side cloud coverage, you can easily see the outgoing flux from the day side peaking near the substellar point. But for slowly rotating planets, which have significant day-side cloud coverage, you wouldn't be able to see this outgoing flux peak near the substellar point because clouds would inhibit the OLR. And so you would actually see an inverted phase curve. And so in principle, we can test all of our theories for cloud coverage on M-dwarf terrestrial planets through infrared phase curves. All right, thank you.
Questions for Tad? You.
Hi, Neil Lewis from the University of Oxford. I was just wondering, in the scaling as you showed it, why you had the presence of the rotation rate, but not the radius? Because in a number of ways, they come into the momentum equations in the same place. Both say, if you're thinking about the equatorial deformation radius, has a beta in it, which has A inside. And also the Rossby number is U over FL, which has an A.
Yeah, so this scaling, I purposely didn't talk about how it's derived. It doesn't come from the momentum equation. It's very, very simple, actually. So it just comes from the slope of an isentrope is related to the scale height divided by the length of an isentrope. And so what we do is we scale the length of isentropes, saying that the maximum length of an isentrope is basically related to an eddy diffusion parameter times the radiative time scale. And so if you can relate that eddy diffusion parameter to large scale properties of the circulation, so if you scale it with, in this case, the Rhine scale, then you can basically then relate that back out to planetary parameters. Does that make sense? So it's very, very simple. Basically, it's just a scaling for these slopes. It's not necessarily a full scaling of the momentum equations like maybe Mark Hammond's done. Yeah.
Down in front.
Mark Hammond, University of Oxford. Are there any observational tests beyond phase curves or other ones that you've thought of for these scaling relations?
Oh, so for the scaling relations, I don't know if phase curves would necessarily be a great test. So for terrestrial planets, I'm thinking about terrestrial planets that are orbiting sun-like stars. So I'm thinking about reflected light with Louvois or Habex in the far future. And so in principle, if the planet is inclined, you can back out an equator to pole brightness difference if you can make brightness maps to the planet. And so that would be really, really challenging. That would require phase curve observations over a long time baseline. But in principle, you could constrain the equator to pole temperature contrast in that case. But more directly, one could constrain the bulk lapse rate through retrieval. So if you have a spectra, you understand, the brightness as a function of wavelength, which tells you a bit about the brightness as a function of pressure, which lets you back out a lapse rate. And so Cat Feng's worked a lot on that.
Quick question, Tad. I mean, if you're looking for reflected light with Louvois and Habex, though, these aren't going to be tidally locked anymore, right?
Oh.
So then you won't have to actually observe them that long because you're looking for a rotation.
Shoot, so I didn't get this across. So the first part, the scaling theory is for planets around sun-like stars that aren't tidally locked.
Ah, okay.
Yeah. So it's not doable in the near future.
Okay.
Yeah.
Cool. Sorry.
Hi, Tad. What? Oh, sorry.
Vivian in the back.
He gave me the microphone. Was that okay?
That's fine.
Okay.
Who are you again?
I'm Vivian Parmentier, Oxford. How does that apply? And can you give me a scaling for hot Jupiters for the equator to pole temperature gradient? Because that's something Emily is going to tell you we can observe with secondary eclipse mapping pretty soon with James Webb, and that'd be great test for the theories. So
that's a really, really good question. So I think most of us are a little unsure how relevant baroclinic instabilities are for the atmospheric circulation of hot Jupiters. I think in a bulk sense, most of the instabilities we see in our GCMs are barotropic, right? Like the shedding of eddies from the equatorial jet, right? And so I'm not really sure if there's baroclinic instabilities in our simulations. It's kind of in a state where maybe they would occur if we had the right forcing setup or something. But in principle, I would expect that warm Jupiters might be more likely to have baroclinic instabilities because they can be faster rotating. And actually, that's what I'm doing next. Right now, we have a summer student who's running warm Jupiter simulations, and we're going to see if this same idea applies to them. So we can test this sooner with James Webb rather than having to wait till the 2040s. Yeah.
Let's thank Tad again.